Alright, what's going on? This video we're going to look at optimization problems. So we've got several examples to work, so let's go ahead and get started. So for optimization problems, typically what you've got is you've got a function that you want to either maximize or minimize. Alright, and more than likely you're going to have two functions. Okay, you'll have the function you want to maximize or minimize, and then you'll have an equation that you're going to use to get the function you're going to maximize or minimize in terms of one variable. All right, so if that doesn't make a whole lot of sense right now, just let's work through some examples and I think you'll catch on. Alright, so it says a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fencing along the river. What are the dimensions of the field that have the largest area? Alright, so let's make a drawing. Let's sketch it. So there's the river, and then we're going to have some fencing right here. All right, so here's the three sides of fencing right here. Okay, these are the three sides. This is the river with no side. So let's label this X and Y. All right, now let's take a look at and see what we have. So it says we have 2,400 feet of fencing. So that means if I add up all three sides, that should equal 2,400. So if I have 2x plus y, that should equal 2,400. All right, so that's some information that I'm given. I've got an equation here, and I want to maximize the area because it asks me what are the dimensions of the field that has the largest area. So what's the area of a rectangle? Well, area is equal to length times width, or in this case x times y. So I want to maximize this, so I need to take the derivative of it. All right, but I want it in terms of one variable. So typically what I like to do is get everything in terms of x. So let's do that. Well, how can I do that? Well, over here I've got 2x plus y equals 2,400. So if I solve for y, I get y equals 2,400 minus 2x. So I can take this 2,400 minus 2x, which that is equal to y, and I can plug it in for y. So I get area, let me switch colors. So area is equal to x times 2,400 minus 2x. And so my area is 2,400x minus 2x squared. All right. Now, the other thing that we want to look at also is we want to write down that x is going to be between 0 and 1,200. All right. Well, why is that? Well, I can't be less than 0. So if I have a number line up here and I have these two values here, well, I know I can't be over here because that would mean the side would be what? It would be negative, and we can't have that. And if I'm more than 2,400, well, I'm sorry, if I'm more than 1,200, well, that would do what? That would that would give me 0. Okay? See, if I set this thing here equal to 0, if I set this equal to 0, well, look at it real quick. 2400x minus 2x squared equals 0. So that's going to be 2. I'm sorry. So I've got 2x times 1200 minus x equals 0. So you can see if I set this equal to 0 and solve it, I get 0 and 1200. So I'm not going to be able to be outside of that. Okay, I'll get values that won't work. So here's my function that I want to maximize. Okay, I want to maximize this area here. So we need to take the derivative. So I've got a prime is equal to 2400 minus 4x. And then what do? Well, we take the 2400 minus 4x, set it equal to 0. I'm finding my critical numbers. And so I get 2400 equals 4x. And so I get x is equal to, let's see, 2400 divided by 4. That's going to give us 600. All right. Now, what's going on here? Well, is this my solution? Well, remember, we're on a closed interval here. So we need to see, is the 600, is that our maximum value? Okay. So do you remember how to do this? We've got a is equal, we've got a of 0. Remember, you test it at the 600, and then you have to test it at each of these endpoints back into, back into the original function. And remember, the smallest values gives you the minimum, the largest values gives you the maximum. All right, so that's going to be, well, a of 0, if I plug that into here, that's going to give me 0. And then a of 600, well, if I plug the 600 in for x, that is actually going to give me 720,000. And then if I do a of 1200, that's going to give me 0 also. So you can see that of the three, the 600 gave me the largest area. So the dimensions of the rectangle would be 600 feet. Let's make sure we're in feet. Yeah, 600 feet by what? Well, remember the 600 feet, that's the x value. Well, now I need the y value. Well, what's my y value? Well, that's this right here. So y is equal to 2400 minus 2 times 600, which that's going to be 1200. So that's by 1200 feet. So that would be the dimensions that gives me the largest area. All right. All right, let's look at the next one. All right, it says a cylindrical can is to be made to hold 1 liter of oil to find the dimensions that will, find the dimensions that will minimize the cost of the metal to manufacture the can. All right. So let's see what we've got. Let's draw a picture. So if I draw a cylindrical can, all right, let's draw the radius, and then we have the height. Okay? Now, let's see what we're trying to find. Find the dimensions that will minimize the cost of the metal to manufacture the can. So that means we want the least surface area. Okay? We want the least amount of the surface area. Now, of course, we're going to have to assume in this problem that the cost to manufacture the cylinder and the cost to manufacture the top and the bottom all cost the same. Okay? So we want to minimize that surface area. All right. Now, first, let's see what we have here. We're going to have two equations, the information that it gives us, and then we're going to come up with an equation on that, kind of like we did up here in this problem where we got the 2x plus y equals 2400. And then we're going to have to come up with a function that in this case, we need to minimize it, like we did here. All right, so let's look. So it tells us that a cylinder is to be made to hold 1 liter of oil. Okay, well, 1 liter is equivalent to what? 1,000 cubic centimeters. Okay, we want to get it in units that we can measure. Height. A distance. So we're going to write the liters in terms of cubic centimeters. All right. All right. Now, what's going to be the function that we want to maximize or minimize? Well, that's the surface area. So what's the surface area? Well, the surface area, call that A, that is going to be the area of the top and bottom. Well, what's the area of the top? Well, the radius is r, so we know the radius of a circle is pi r squared. And then that's going to be times 2 because we have the top and the bottom. We have 2 circles. And then plus the surface area of what? The actual cylinder. Okay? So what's the surface area of the cylinder? Well, remember that if you take a cylinder and let's just assume we just kind of cut it right here and we fold it open, that's just going to be like a rectangle, right? See, this top here, when it unfolds, it'll unfold to this straight side here, and then here's the height. Well, what's the distance of this right here? What's that distance there? Well, it's the circumference of that circle. Okay, it's the circumference of the circle. And the circumference of that circle is 2 pi r, or pi times the diameter, or 2 pi times the radius. Okay, all this 2r is just doubling the radius for the diameter. Okay, and then this distance here, that's the height. So times h. All right, so there's our function right there. Now, it does tell us that the volume, okay, the volume is 1 liter or 1,000 cubic centimeters. Well, what's the volume of a cylindrical can? Well, the 1,000 is going to equal to, well, what's the volume of this thing? Well, remember the volume, if you take a cross section, okay, so in other words, like say if you cut this can in half here and you look at it from the top or bottom, it's going to be a circle. So the volume would be the area of the cross section, which is pi r squared, times the height. right? So what this is going to do is this is going to help us get our function that we want to maximize or minimize in terms of one variable, because you can see up here we've got it in terms of R and H for our variables. So let's get everything in terms of R. So I need to know what H is in terms of R. Well, here I can see H is 1,000 over pi r squared. So I can replace H with 1,000 over pi r squared. So A is equal to 2 pi r squared plus 2 pi r times 1,000 over pi r squared. And so the area is 2 pi r squared plus, and let's see, what is that going to be? 2,000 over r. Okay. Now, what do we know about this? Well, we know that r is positive, right? R can't be negative. It's going to have to be larger than 0 because the radius can't be negative. So if I take the derivative, I get a prime is equal to 4 pi r minus 2,000 over r squared. So remember, the 2,000 over r, if we take the derivative of that, 2,000 over r, we take the derivative, well, what would that be? That would be 2,000 r to the negative 1, and then we just use the power rule. Negative 2,000 r to the negative 2, and then that would be negative 2,000, and then move the r squared down there to the denominator. Okay, and that's where that 2,000 r squared comes from. All right. And so now what do? Well, now we set the derivative equal to 0. So, I'm going to do that here. I got 4 pi r minus 2,000 over r squared equals 0. So 4 pi r equals 2,000 over r squared. And so I get, let's see, r cubed is equal to, what is that, 500 over pi. And so r is equal to the cube root of 500 over pi. All right, so now what can we do? All right, well, let's look at maybe, I don't know if we can do something to maybe simplify this a little more. I don't know, maybe we can, maybe we can't. Let's look and see what we've got. All right, so I don't think there's much else we're going to be able to do with that r. So that would be r. Now, well, we need to what? We need to know the dimensions of the can. And look, and we can show that this is a minimum. You can do your number line. Okay, you can do your number line and everything, and it'll show that it's a minimum. You know what I mean? When you take the cube root of 500 over pi, and you choose a number over here, choose a number over here, and it'll show here it's decreasing and here it's increasing. Okay. All right. So anyway, let's find h. All right. So h is equal to this. So we need to plug r in, what we got for r, which is the cube root of 500 over pi. So h is equal to 1,000 over pi times the cube root of 500 over pi squared. All right. And so this is going to give us 1,000 over pi times 500 over pi to the 2/3. I just converted the radical into exponential form. Now let's see if we can simplify this a little more. All right, so I noticed the 1,000. I can write that as 2 times 500, and that's over pi times 500 over pi to the 2/3. And then if I separate this out, you see this 500 over pi here, and then this 500 over pi to the 2/3. Let's write this as 2 times 500 over pi over 500 over pi to the 2/3. All right, so this right here is the same thing as this. Okay, I just separated it out. I've got the 2 away from, got the 2 out here, and then this 500 over pi, this 500 and this pi, just wrote it up here in the numerator. Well, this is 2 times, and that's going to be 500 over pi to the what? To the 1 minus 2/3, which that's going to be 2 times 500 over pi to the 1/3, which is going to be 2 times the cube root of 500 over pi. And so I can actually write the height as what? 2r. Okay, there's your height, and there is your radius. Okay, now where did the r come from? Well, what's r? It's the cube root of 500 over pi, and I just replaced the cube root of 500 over pi with r. All right. So hopefully that made sense. All right, let's look at this one. We've got, it says, find the point on the parabola y squared equals 2x that is closest to the point 1, 4. All right. So let's see what we've got here. So first thing we want to do is let's sketch the graph. And you know, when you sketch this, it doesn't have to be, you know, you don't have to just draw it exactly, you know, just sketch it close. And so we know this is a parabola that's going to open to the right. We got the y squared here. And our point 1, 4 is going to be up here. That's 1, 4. This, we want to find a point on this graph that's closest to that point right there. You see that? That's closest to that point. All right, so let's think about this for just a second. Well, here's my point xy. Okay, some point xy on the graph. What's that point? I don't know. Okay, that's what we're gonna figure out. But what do we want to do? We want to minimize this distance here. Okay, that's what it's asking for. Find the point on the parabola that is closest to the point 1, 4. So we want this distance to be a minimum. So if you remember back from algebra, if you have 2 points on a graph, say x1, y1, and x2, y2, remember the distance between the 2 points is x2 minus x1 squared plus y2 minus y1 squared. Okay, that's the distance between 2 points. So let's do x2 minus x1 plus y2 minus y1. So the distance we have is the square root of x2 minus x1 squared plus what? y2 minus y1 squared. Okay, I'm calling this x2 y2, and I'm calling this one x1 y1. And now we're going to what? We're going to take the derivative. But before I take the derivative, okay, what do I need to do? Okay, what do I need to do? Well, I want to get everything in terms of one variable. I want to get everything in terms of x or everything in terms of y. Well, in this problem, I think it might probably be easier if we got everything in terms of y. Let's do that. So I would have the distance is equal to the square root of 1/2 y squared minus 1 squared. Okay, so, well, where did that come from? Well, you can see here x is equal to 1/2 y squared, okay, based on our function here, or our equation we have up here, y squared equals 2x. So I'm just replacing the x with this 1/2 y squared, and then that's plus y, and then that's plus y minus 4, and then all of that squared. All right, so what do we need to do now? We need to take the derivative, right? All right, so to take the derivative, I don't know if you've watched a lot of my videos, but I have a video out on shortcut for finding the derivative of a square root. So what you can do, and I'm going to just do it right here, d prime is equal to, all right, so look at this. So the derivative of a square root, there's a shortcut. It's just 2 times the square root of 1/2 y squared minus 1 squared plus y minus 4 squared. So whenever you're taking the derivative of a square root, it's 2 times whatever your square root is. Okay, that goes in the denominator every time. And then what goes in the numerator is the derivative of what's underneath the square root. So what's the derivative of what's underneath the square root? Well, I've got chain rule here, right? So the 2 comes down times 1/2 y squared minus 1, subtract 1 from the exponent, so that's to the first power, times the derivative of what's inside the parentheses, which in this case is just y. And then plus, chain rule again, 2y minus 4, that's to the first power, times the derivative of what's inside the parentheses, which is 1. All right. And so now all I need to do is just distribute, clear the parentheses here, combine like terms if I can. So let's see what we get. So this is going to be y cubed, right? Let's see. Yeah, y cubed minus 2y plus 2y minus 8 over 2 square root of 1/2 y squared minus 1 squared plus y minus 4 squared. All right, so this is going to give us d prime is, well, that worked out nice, didn't it? Y cubed minus 8 over 2 square root 1/2 y squared minus 1 squared plus y minus 4 squared. All right, now what do we want? What do we want now? Well, remember, you got to set this equal to 0 and solve for in this case, y. All right, so we know that a fraction is 0, okay? So we know d prime is 0 when y cubed minus 8 is 0. So y cubed equals 8 and y equals 2. All right. So look, you can test this. You can put the 2. We can do x equal 1. We can do x equal 3. And just keep in mind the denominator is going to always be positive. So if we plug the 1 in, that's going to give us a negative. We plug the 3 in, that's going to give us a positive. And you can see y equals 2 is a minimum. Okay. And so this is the y coordinate of the point we're looking for. Well, now we want what? We want the x coordinate of the point. Well, what was our function? Let's see. Our function was y squared equals 2x. So if I plug the 2 in for y squared, that's going to be 2 squared equals 2x. So we get x is equal to 2. And so that's the point. That's the closest. This is the point on the parabola that's closest to the point 1, 4. Okay, that would be this point here. This would be the point 2, 2. All right, so you know that it wasn't too bad. I mean, it got a little messy on the derivative, but it's not bad. I mean, you know, luckily it came out like this. This made it nice there. And then, of course, a fraction is just 0 when the numerator is 0, so we didn't have to worry about the denominator. All right, what about this one? All right, so for this example, we have a man launches his boat from point A on the bank of a straight river 3 kilometers wide and wants to reach point B 8 kilometers downstream on the opposite side of the bank as quickly as possible. He could row his boat directly across the river to point C and then run to point B, or he could row directly to point B, or he could row to some point D between C and B, and then, that should be then there, and then run to B. If he can row 6 kilometers an hour and run 8 kilometers an hour, where should he land to reach B as soon as possible? So the best thing here is going to be to draw a picture. So if we, what happened there? Let's see. All right, so if we draw the river, and he launches his boat from point A, and we know that the river is 3 kilometers wide, and he wants to reach a point B 8 kilometers downstream on the opposite side of the bank. So that would be a point B right here, and it is 8 kilometers downstream. All right, so it says he could row his boat directly across the river to point C. So that means he would be going straight across to some point C. And then, so he could row straight across and then run down. Or he could row directly to B. So that's from A directly to B. He does nothing but row. Or he could row to some point D, which we'll call this D here, that's between C and B, and then run to B. All right, so how far would this point need to come down? Well, let's see if we can figure that out. We'll call that X, and so we know this distance here is 8 minus X. All right. So what we want to do is we want to minimize the time, right? We want the shortest time. Well, how are we going to do that? Well, we know that distance is equal to rate times time, which tells us that time is equal to distance over rate. All right, so that's what we're trying to minimize is time. So we need distance and we need the rate. All right. So if we draw a line from A to D, all right, what would this distance here be from A to D? Well, remember, this is a right triangle. So this side here would be x squared plus 9, right? So if we write down rowing, the time it takes him to row, that would be what? The distance, which is this distance here from A to D, which is the square root of x squared plus 9, over the rate. Well, how fast does he row? He rows 6 kilometers per hour. So that's the time it's going to take him to row. Now, what about running? How long will it take him to run? Well, what's the distance he has to run? That would be 8 minus x over the rate that he runs. Well, he runs 8 kilometers per hour. So this is the time it takes him to row. This is the time it takes him to run. So we need that total time. So we'll call that t of x is equal to the square root of x squared plus 9 over 6 plus 8 minus x over 8. All right. So there's our time. So we need to take the derivative, right? We need to take the derivative. But before we take the derivative, I want to do something real quick. It'll make it a little bit easier to see how we take the derivative. So that's 1/6 square root of x squared plus 9 plus, and then this is 8 over 8, which is 1, minus 1/8 x. I just split this fraction up. All right. So I think writing it like this, it'll make it easier to take the derivative. So we have t prime of x is equal to 1/6. All right, so remember earlier we took the derivative of square root, used that little shortcut. So the shortcut to take the derivative of a square root is just 2 times the square root. Okay, so remember it's 2 times whatever this is, and then what goes in the numerator? The derivative of what's underneath the square root, which is 2x. And then the derivative of 1 is 0, and then the derivative of minus 1/8 x is minus 1/8. And so we get t prime of x is equal to x over 6 square root of x squared plus 9 minus 1/8. So all I did there is I canceled the 2's. All right. Now, we need to set this equal to 0 and solve for x. So if I got x over 6 times square root x squared plus 9 minus 1/8 equals 0. So I get x over 6 times the square root of x squared plus 9 equals 1/8. All right, so solving this, we're going to get, let's see, what is that going to be? That's going to be 4 over 3x equals the square root of x squared plus 9. I just moved the 8 up. 8 over 6 is 4/3. And then this square root of x squared plus 9, I just moved it to the other side. Then we're going to square both sides. So that's going to be 16 over 9 x squared equals, and that's going to be x squared plus 9. Now, well, let's see what happens. Maybe if I multiply everything through by 9, get rid of those fractions, that's going to be 16x squared equals 9x squared plus 81. And so I get 7x squared plus 81. Equals 81. And so x squared equals 81 over 7. And so x squared equals 9 over square root, not x squared. X equals 9 over square root of 7. All right, that's our only critical number. All right, now keep in mind, when I go from this step to this step, it is plus or minus, but we know it's not minus, okay, because that distance can't be negative, so we only use the positive. All right, so we've got 9 over square root of 7. Now let's come back up here real quick. So let me just write that. X equals 9 over square root of 7. Now, the one thing we've got to look at here is that we're on the interval 0 to 8. See, that's all that x can be. X can be 0, so that means we would just go straight across. Or x can be 8. And if it's 8, that means we go directly to b. But it can't be anything less than 0, and it can't be anything more than 8. So we have a closed interval here. So we've got to take all three values, the 9 over square root of 7, the 0, and the 8, and we have to plug it back into the original equation to see which one gives us what? The smallest value. Okay? So if I do t of 0, and I'm not going to show me plugging the numbers in, but t of 0 is 1.5. T of 9 over square root of 7, that is 1.33. And t of 8 is equal to 1.42. And you can see of the three that we evaluated, that's our smallest. So that means x is equal to 9 over square root of 7. And that's your answer. All right. All right, so let's take a look at the next problem. All right, so find the area of the largest rectangle that can be inscribed in a semicircle of radius r. All right, so let's draw a picture. Okay, so we draw a picture. So if I draw the semicircle, it's going to be right there. And this right here is I'm drawing it in the middle. Okay. And so we know that this is r, this is negative r. Okay. That's the radius of the circle. And so now if I draw me a rectangle in here, I want the largest area for the rectangle. All right, so we can have a point here, xy. So I know this distance here is y. This distance here, it goes out x units. And from here, it goes out x units, right? It goes x units this way, x units this way. All right, because if I plot the point x, y, x, y. And so what do we want to maximize? The area. Well, what's the area of this rectangle? Well, the area is length times width. So see, that's 2x times y. Well, now we have to do what? We have to take the derivative of this thing, don't we? You see that? We've got to take the derivative. So I need to somehow get this area here all in terms of x or all in terms of y. Well, to get rid of the y, we can use the fact that we know this point here, this point xy, lies on the circle x squared plus y squared equals r squared. Remember that from algebra? When you're finding the equation of a circle. See, we place the center of the circle here at 0, 0. All right? And so if we solve this, we get y squared is equal to r squared minus x squared. So y is equal to the square root of r squared minus x squared. Now, that's plus or minus, okay? That's plus or minus here, but we use the positive because we're using the part that's above the x-axis. If we were drawing it down here, we would use the negative. So we have y is equal to this. So we can replace this y with this. So we got area is 2x times the square root of r squared minus x squared. Now, what's the domain of our function? Well, that's going to be what? 0 less than or equal to x less than or equal to r. Okay? Because, you know, for one thing, we can't have a negative underneath the radical. All right. So now we have to take the derivative. So the derivative, well, this is product rule. I've got 2x times the square root of r squared minus x squared. So the derivative of the first function is 2 times the second function plus the derivative of the second function. And once again, here's a shortcut for finding the derivative of a square root. And then what goes up here? Negative 2x. Okay, see, the derivative of what's underneath the radical is negative 2x, and then times the first function, so times 2x. So I get a prime is equal to 2 square root r squared minus x squared minus, what is that? Is that 2x squared over the square root of r squared minus x squared. All right, so now let's set this thing equal to 0. So I'm going to get 2 square root r squared minus x squared minus 2x squared over the square root of r squared minus x squared equals 0. So I'll just move this over. So that's going to be 2 square root of r squared minus x squared equals 2x squared over r squared minus x squared, square root of that. And so then I can multiply. But look at this. I can cancel those 2's out. You see that? And then if I multiply this times this, that's going to give me r squared minus x squared equals x squared. And so I get r squared is equal to 2x squared. And so that's going to give me x squared is equal to r squared over 2. And so x is equal to what? R over square root of 2. All right. And this is going to be a maximum. Okay, this is going to be my maximum. And also, remember, we're between 0 and r. Remember this up here? We're between 0 and r. So, I mean, you know it's a maximum. This is positive, right? We know this is positive because r is positive, square root of 2 is positive. So if we do if we do a of 0 and a of r, I mean, just look at this up here. A of 0. So if I plug 0 in here, see, that's 0 times whatever that is 0. And then if I plug r in, that's r squared minus r squared. That's 0. And so that makes the whole thing 0. So both of these are equal to 0. And so we know this gives us our maximum area. Now, remember, let me erase this. They want to know what is the maximum area. That's what they're asking for. So what I'm going to do is I'm going to grab this and I'm going to pull it down here so we can see the function. All right. So the maximum area is equal to, well, I'm going to take this and plug it in for x. So that's 2 times r over the square root of 2 times the square root of r squared minus r over the square root of 2. And so that's going to be 2 times r over square root of 2 times the square root of r squared minus r squared over 2, which this is going to be 2 times r over the square root of 2 times the square root, now r squared minus r squared over 2, well, that's just r squared over 2. So this is going to be 2 times r over square root of 2 times r over square root of 2, which is 2r squared over 2, which is r squared. And that is your maximum area. All right, so, you know, doing these optimization problems, it's not that bad. The main thing is getting that function that you're trying to maximize or minimize and getting it all in terms of one variable and then taking the derivative. That's all you're doing. All right. So I hope this helped. I've got more videos on optimization problems. There's a bunch of videos I have. It's just one problem per video. This right here is just a bunch of problems in one video. All right. But if you want to look at some different kinds of problems, just search my channel for optimization and a bunch of them will come up. So I hope the video helped. Check out my other videos. Give me a like, share, and subscribe. Thanks for watching, and I'll see you later.